Our final speaker this evening is Hansol Hong, currently at Harvard and Brandeis, but in residence at Harvard. He's going to tell us about mirror symmetry for punctured Riemann surfaces and gluing construction.
Thank you very much. So I first like to thank the organizers for inviting me. And today I'm going to talk about something very, very simple, at least simpler than what we have learned in the previous lecture, which is we're going to talk about Riemann surfaces, punctured Riemann surfaces, the mirror symmetry of punctured Riemann surfaces, homological HMS for punctured Riemann surfaces. And there are lots of works about mirror symmetry for punctured Riemann surfaces, like the Oru, Abujai, Oru, Kasarkov, Efimov, and also Abujai, Oru, Efimov, Kasarkov, and Oru. So they proved homological mirror symmetry for punctured spheres. And there's work by Heather Lee. Proved the homological mirror symmetry of punctured Riemann surface using like gluings and so on. And there's another work by Laf Bockles, which uses dimer quivers on the punctured Riemann surface and all these combinatorial data. And he also used this combinatorial data to construct a mirror and so on. So I'm going to review what he has done and give a different interpretation using the discounting of certain Lagrangian of the punctured Riemann surface. So let me do some review of Bockles. So here the dimer is nothing but the quiver which is drawn on the surface. So definition. So dimer is a quiver on a surface, on a Riemann surface. Riemann surface. Sigma that splits the surface into polygons in a nice way. Into polygons. A nice way. So what do I mean by being nice here? I'll give you one example. So let's look at a four punctures here. So here the quiver is drawn on the surface, and I'm going to regard the vertices of the quiver as a puncture of the surface. So the example is this sphere. So I'm going to label the edges in the following way. So I have x, and here the x2, and y, z, w. And you somehow form this rectangle on the right hand side, and identify these two pair of edges to get a punctured four punctured sphere. So these vertices of the quiver are thought of as punctures of the Riemann surface. Okay. And here, being nice means you have faces, and each face, you look at the orientations of the arrows, of the edges, and it's either coherent with the orientation of the surface or completely opposite to the orientation of the surface. So this is what I mean by nice here. And if you, let me continue this example. If you have this is called dimer. I call it Q. And if you have a dimer, then there's a so-called dual dimer. So how to construct it is simple. So you have the positive phase here and minus phase here, meaning the orientation is positive. with respect to the boundary orientation of the surface of the face, and here negative. And you cut out the negative face and flip it, and reverse the order of the arrows, and then you throw it back. So you keep the plus face, the positive face, and you cut and flip and glue back. Then you get the following: a new Riemann surface and the dimer. So here I reverse the arrow, the order of arrows. Here W, Z, Y, X. Originally I had X, Y, Z, W. And if you glue this a diagram very carefully, then you will see this is actually two punctures here. As I said, these are all punctures. And this is actually two punctures. Okay. So yeah, this is so-called dual dimer. And you may wonder if this construction is possible for a more complicated configuration. And there's actually more formal definition of dual dimer using so-called zigzag cycle. And maybe some rough definition of dual dimer would be the vertices of Q check is a so-called zigzag cycle. These are elements in the path edge of the original Hilbert cube. And also give you, I explain this by giving an example. So like I can show it here. So I draw a twofold cover of this picture to see this zigzag cycle more clearly. So the diagram is something like this and this. Oh, sorry. So this is twofold cover, but yeah, what I'm considering is it's still the same example. And then what is a dual? What is a zigzag cycle here? So zigzag cycles is a cycle in the path algebra, and you take one point here. These are like positive phase and negative positive. So you first go along the positive phase for 2 steps. And then the next step is you go along the negative phase, like this. And then positive phase again. And if you do this 1, 2, 3, 4 times, then you come back to the original point. So these two are the same point. As I said, this is double cover of this picture. So this kind of thing is called zigzag cycle. And there is actually one more. Which start from here, the same points. But you first go along the negative phase. So you go this way, and then you go along positive phase and the negative phase, and then you come back. So there are 2 zigzag cycles, and here you see 2 vertices as well. So here, I think these 3 vertices should be the same by this identification. And the yellow one is right here. I could be wrong. Either this or the other way around. So vertices are zigzag cycles, and what is the arrows? So arrow is an intersection of zigzag cycles. You see, actually these 2 zigzag cycles intersect each other a lot of times. So first intersection is here, right? So this is Y, this is W. So that's why you see this arrow. So whenever there is an intersection, you join them by and then label this edge arrow by this intersection arrow of zigzag cycle. This is this intersection of zigzag cycles. So yeah, this is like another definition of taking dual dimer. And what Vauquelin proved using a dual dimer is the following. So you have this dimer model on some punctured Riemann surface, and then there's some. So you do some combinatorial data of this dimer, gives you two cyclic words. So you do some combinatorial data of a dual dimer, Q-chat. Will give you two cyclic words, which are called B and W. So Volkmann defined phi and W using purely combinatorial language of the dual dimer here. But later I'm going to define these two cyclic words using Lagrangian floor theory and deformation theory on the Lagrangian circles. So yeah, I'll just leave it like this. I'm not going to define this using like Keeper data and so on. So anyway, there's a way to produce these two words. And these are basically counting of like cycles and phases and so on. And then the theorem is given to prove the mirror symmetry of a punctured Riemann surface, which is sigma minus, as I said, the vertices of the quiver will be got up as a punctured of the Riemann surface. And look at Crank category. And here you have path algebra. And then you divide this by the Jacobian ideal ring of this cyclic word, the first cyclic word. You get some non-commutative algebra, and then here's some element W. And then this is actually central element. So this kind of Gazit is called non-commutative under Ginsburg model, and he looked at matrix factorization of W. And he actually didn't prove they're equivalent. So he picked up some small subcategory here called small f, generated by arrows of this dimer, which are non-compact. And here he also picked up very small set of objects and called it small n, and then derived it. And then he proved this equivalence holds. And yeah, this is purely a combinatorial description of like how objects should match with each other and how Morphism space should map to the other side and so on. And now I'm going to show you how to interpret his result using the Lagrangian floor theory of certain Lagrangian on this surface. So yeah. So I'm going to define so-called something called zigzag Lagrangian. So you may already notice this zigzag cycle is somehow a kind of compact object, or it's compact circle or something. You can assign a Lagrangian circle for each zigzag cycle in your keyboard in the following way. So I'm going to call this zigzag Lagrangian. So in general, if you have zigzag cycle like this, and the most natural way you can think of is probably you take the midpoint here, and you join that and smooth it a little bit at each corner. Then you get some smooth curve like this. Right? So this I call zigzag. So let's come back to this example. Maybe I'll draw the one here. So you have one here. So for example, this one gives you a circle, and the other one. Other ones gives another circle, and you'll see this intersection of two zigzag cycle corresponds to intersection of two Lagrangians. So yeah, I draw a more precise picture here. So you have again, my example is sphere minus 4 points. And to do this construction, you get two Lagrangian circles, which is one is this guy. The other is this guy. And they intersect each other at four different points. And for your imagination, I may draw a 3D picture as well. So this is this. And one Lagrangian is this circle. And the other one is the reflection image of this guy. So it's not the reflection image. Sorry. Yeah. Maybe. Okay. Is that right? Yeah, maybe I better not draw it. Yeah, anyway, something like this. So you have two circles on four sphere minus 4 points, and they intersect each other along at four different points. And I'm going to label them by x, y, z, w according to the labeling. X, y, z, here the same x, y. Let me just quickly erase it. Probably wrong. And now you have this set of Lagrangian circles. You're going to denote this by bold L, which is a union of L1. This is L1. This is L2. So L is my bold L is L1 union L2. I'm going to study the formal deformation of this Lagrangian by this immersed points. Geometrically, this formal deformation would mean like smoothing out all these corners. You will see. So first of all, if you have this set of Lagrangians, you can naturally draw some quiver. So you have two Lagrangians, so you have two vertices, 1 and 2. And for each degree 1 intersection, you draw an arrow. So for example, here xw, x and I think x and w, x and g, z are degree 1 intersection between 2 and 1. You have two arrows. This is c and w, meaning c, this big C and w is an element, degree 1 element between from 1 to 2, from 2 to 1, 2, 1. Likewise, you have degree 1 intersection points from L1 to L2, which are x and y, x and I'm sorry, y and w. This should be x. And here you have y and w. So this is exactly a definition here, right? So for each zigzag cycle, I have Lagrangian. And for Lagrangian, I put one vertex, right? And for each intersection of zigzag cycle, I have intersection of my Lagrangian circles. And for those intersections, I draw arrows here. So as a quiver, I'm going to denote this a quiver by Q to be QL. And as a quiver, this QL is exactly the same as Q check. But I don't need a dimer structure on it because I'm going to read off all this combinatorial data from Lagrangian floor theory on this side. So yeah, so we study the formal deformation of L, fold L, by deformation parameter B, which I define to be XX and YY, CZ, and WW. So here, these big letters, X, Y, Z, W, are intersection points, or self-intersection points of fold L. And these variables, X, Y, Z, W, are formal variables from the path algebra of this figure. So this is from gamma QL. A priori, they don't have any relation among them. But they, after solving some equation, it's called Witt-Maurer-Kaplan equation, you'll see they should have some relation to determine meaningful deformation, meaningful formal deformation. So what do I mean by formal deformation here? So you solve this equation. You solve Maurer-Kaplan. Which is M of B to B. This is notation. This is M1B, this is M2 BB. And you want this to be usually 0 when you study this usual deformation theory. But here I'll study a formal weak deformation of Lagrangian. So I want this to be some constant W times the unit.
There's no M0?
There's no M0. And there's no M0. Okay, originally I should have to put M0 here as well, but in this example we don't have M0. Okay, maybe I'll do M0. Which is 0 in this example. And I want this to be some constant times unit of this Lagrangian. And of course, this constant will depend on B as well. And such a function on the space of B will be called superpotential. So let's try to solve this equation. So whenever you have this B, we can deform the A-infinite structure on the forward complex of this Lagrangian L in an algebraic way. And that's what I mean by formal deformation. But you have to first solve this equation, otherwise you'll get some awkward deformation. So let's just solve it for this example. And this is nothing but discounting, and of course I'm looking at punctured units. It's extremely simple. So if you compute this, then what you can see is these rectangles and no other disks, right? Because so you may have some number times the unit of the first Lagrangian. So this number will come from M4. If you do M4, then you get the evaluation will be on the edge. So you get a unit of one of the Lagrangians, and the same term will be here too in L2. So this is rather good because you want the whole equation to be something times unit. You already have something similar to unit, but you have more here because, for example, M3 of XYZ will be W, or M3 of XWZ will be Y, and something like that. So we'll have, for example, you may have W bar. The W bar means the W is an element in L1, L2, L2, L1. I'm sorry, L1, L2. The W bar is the same point, but regarded as a form from L2 to L1. So you may have W bar, and the coefficient will be these formal variables, the monomial consisting of these formal variables. So you see, in floor theory, you always read of the variables in one direction, the counterclockwise direction. So in this, from this rectangle, you get x, y, z, right? I'm not going to explain a sign rule, but somehow the other triangle, the other rectangle will give you minus sign. you have to you still have to read this in counterclockwise order. So you get C, Y, X now, not X, Y, Z. So this is from M3. And you have 3 more terms from Y bar, X bar, Z bar, and so on. So what you want is this, right? So the whole equation to be something times unit. But now you have something undesired. So let's just kill it by quotienting out the algebra by this relation. So how? So originally you have this path algebra, and then you impose this relation, this to be 0, and so x, y, z minus c, y, x equals 0. And you have 3 more. And now this will be my my base algebra, and you pick up a variable from this algebra, call it maybe a. So you pick up x, y, z, w from here. Then you compute this again. So for this x, y, z, w, m to be eb, which is m1b, m1b plus m2eb, so on. Will be now you kill all the terms here because of this relation. Will be something times unit. So you have to check it actually. You have to compute it, but because I don't have much time. So this is actually something times unit, and this is this color here will be just x, y, z, w. So you have a weakly unobstructed Lagrangian, meaning the Lagrangian in B that solves this equation, and you have a potential x, y, z, w. So this will give you a mere Landau-Ginzburg model, A, comma. So one remark here is that this guy, the relation is actually a Jacobian ideal of certain phi. This is partial I of phi generated by the partial derivatives of phi. Here phi is given by x, y, z, w, z. So now it's clear why we have to flip the negative phase when you construct the mirror qubits. Because the XYZW is a cyclic word on the original qubit, but not the second one. The WZYX is not a cyclic word in this qubit. So that's why you have to flip the negative phase. Although I only drew a qubit here, but if you remember the construction of dual dimer. So this explains somehow why you have to flip the phase when you construct a mirror. Anyway, this is a mirror Landau-Ginzburg model. And the theorem will be this joint work with Cho and myself. We have an A-infinite functor from chi category, the red chi category, of the same thing, the punctured Riemann surface, to the matrix factorization of this W. And if you restrict this functor to these small categories that Vauquelin has considered, then it's exactly the same. This gives exactly the same functor. This is more information in some sense because first of all, this is defined over the whole red category, and I have higher functors as well. So yeah, this defines a triangulated functor when you derive both functors. And then the remark is this type of construction works in more general cases. Say you just have some symplectic manifold and set of Lagrangians. And you can always construct this pure and some non-commutative Landau-Ginzburg model and this functor. But just
So here you expect an equivalence, right?
Yeah, expect equivalence, but the problem is that the mirror side is non-commutative. It's hard to find the generators of non-commutative matrix factorizations and so on. But yeah, I just want to tell you this kind of construction works in much more general setting. But whether this functor is an equivalence or not, it's hard.
Do you know
to
it's
say.
fully faithful?
Yes, it's not. Yeah, it's in general it's not fully faithful. But what I know is the mirror is constructed from certain Lagrangian bold L. And if you restrict this functor to Hom LL, to its mirror image, and this is always injected in any case. But yeah, this is. Yeah, I think this is fully faithful in this example, but in more general setting, still we can prove this map is always injective. Yeah, I did check this.
So the left-hand side, can I think of this as like a special case of the our rules instruction for the complement of divisor? Is this
SYZ fibers
Yeah.
and so on?
Yeah.
Yeah, kind of, because in Oru's setting, he studied like geometric deformation of Lagrangian force fibers. But here I study formal deformation, not geometric deformation. It's somehow the similar philosophy, but we're not.
yours is kind of like the infinitesimal version, is that?
Kind of, yeah. So as I said, the right-hand side is usually non-commutative, and it's just pretty hard to understand. So yeah, and the question is, instead of having this mirror, not mirror, but complicated non-commutative mirror, can we have commutative mirror instead? And, in this example, for punctured sphere, you can do some detour in the following way. So begin with this is summary of what we did in this example. So we have this four punctured sphere, and I took certain Lagrangian here, and I constructed a quiver, which is simply this. And I looked at this packed algebra, and I take a portion of this algebra by a certain relation. So this was my A, and then there's a potential. And so if you restrict yourself to loops at one vertex, then you will see this is actually non-commutative resolution of conifold. So this is there is a conifold. And relation between these two is like this conifold is really looking at loops at one vertex. So for example, this relation force. So you have like x, y, x, xc, y, w, and more xc. X and Y, XY, sorry, Y and Z, and XY, XW, and CW. So if you look at loops based at one vertex, then these are the path algebra, the loop algebra was generated by these four variables. And from this relation, you will see these are commutative variables. And then they satisfy this conifold relation. So this is how you get back the commutative thing. And this potential will descend to the conifold as well. And then you do a commutative resolution this time. So this is non-commutative Krepan resolution. And this is now we take toric Krepan resolution. And you get all P1 minus 1. So P minus 1. Plus the potential. You can lift it too. And this is kind of weird. And this guy, the Krepan resolution, is actually the mirror which was obtained by Oru AAEKO. same as the meter obtained by AAEKO. And now the question is whether you can get this space just directly, not getting around like this. It's just work in progress, so it's not like complete. I'll just show you a rough way to get this space directly now. Okay. The question is, can we get a little bit nearer, more directly? So I make one observation. Is even for this construction, this pivot construction, there is a case when you can get the commutative meter, which is a pair of pens. So this is a pair of pens, or a sphere minus 3 points. And as a quiver or as a dimer, I use these three arrows. One. And then if you draw a zigzag Lagrangian, then you get a certain inverse circle. It looks like this. And you have three self-intersection points, x, y, z. And you compute the Wick-Maurer-Cartan equation and so on. Then the relation will be like xy equals yx and yz equals zy and so on. So if you apply this construction the same way, then you get the commutative space, C3. And the coordinates is xyz. And the potential is this xyz. So this is one observation. And now let's go back to a little more, slightly more complicated example, which is 4 punctured sphere. And I draw this 4 punctured sphere in the middle. So decompose 4 punctured sphere into 2 pair of pens. It's a pair of pens. And these are actually punctures, although I drew it in this way. And if you glue these two, then you get back the four punctured sphere. And the good thing is each chart or each piece, you have a commutative meter. So the question is, can we whether we can glue this? And there is a work by Heather Lee. So I should mention there's a similar work by Heather Lee in a similar flavor. So Heather Lee actually do this gluing construction. For replica category for each piece. So she glued a replica category of each piece, and also she glued the local meter piece by piece, and she proved the SMS for punctured dimensions. Anyway, yeah. So we also want to do the similar thing by gluing these 2 local charts, because at least we know this each local piece produce something commutative, which is D3 and W equals X1. So draw 2 Lagrangians here. Here as well. For each piece, you have this thing. Here you have C3 and X prime, X, Y, Z. So label these points by X, Y, Z here. X, Y, Z. And here say X prime, Y prime, Z prime. And you get another C3 here, and X prime, Y prime, Z. Which is like a local. Here, X prime, Y prime, Z. And to glue this, you have to compare the flow theory information of these 2 Lagrangians, which which looks pretty hard at this moment. So I'm going to do some surgery here so that these two figure becomes more similar. So you take the surgery here. Then the local picture is, I'm not going to draw this part. So if you do a surgery here, then this immersed circle breaks into a union of two circles. So you get one is this, the other is this, the other is. Do the same thing here. So now you take the surgery at this point. Then you also have a union of two circles. Now our picture looks pretty much the same with each other. So you can propagate the information from this guy to this guy. So after taking surgery, there is a little change because now I lost my x. So you want to keep track of this information of x. So instead of considering this immersed point, now you have two special points, which go back to x, the original picture. And now I'm going to consider the holonomic deformation instead of deformation by immersed points. So here I have holonomic deformation. Parameterized by t. The holonomic deformation means if you have a strip or holomorphic disk that passing through this point, then you just multiply this complex number to the output. So this is holonomic. But now the difference is you can consider e to the minus t as well. Right? So here x is not invertible variable, but once you turn this into holonomic deformation, now this becomes invertible. So now the local piece is not C3, but here you see C star. But other two variables are the same, y and c. Because I turned one immersed sector into holonomic deformation. And here you have the same thing, C star times C2. So you exactly the same thing, and you can compare two configuration just by hands. So yeah, the question is how to identify them. And now you can use a local information of the potential. Right? So here, the problem is they're not exactly the same. If you do the surgery at this point, then you also have two special points of the holonomic deformation. One is here, the other is here. So if you glue this point back, then you get the same x prime, y prime, z prime. So they're slightly different because the representative of these flat connections are different. Here, special points are here. And for this Lagrangian, special points are here. So how to connect them? You can use the information of the potential. Because it's not like just gluing the spaces, but you also want to have a global function W on this glued mirror space. So let's just keep track of how potential changes. Now you have here you have x, y, z, right? And then here, now I change x into e to the t. And you count this, and this x, y, z is actually from this part. And you get here e to the t and y, z. Okay. And let's move one of the points. Maybe this point to here. So eventually you have to move 2 points to the other side to get the same picture on the right hand side. So let's do it one by one. And let's first move this point to the back. Then what you have is the same Lagrangian, but one point is one special point representing the is now on the back. And one point is the same. The original, the first point I do it in the second step. So this is like in the middle step, and you have y and z. But now you look at this strip, and you see there is no holonomic deformation on this strip. So here w will be but something has to be changed, right? So our convention is because these points passing through this immersed sector, so you have to do some adjustment to this point as well. Here I made some coordinate change, but to figure out what y prime is, you have to look at w, which is in this case just y prime. See. So you compare these two. You see y prime should be and you can keep doing this, and eventually you keep doing this, and you move this point back to the opposite position to get this picture. And yeah, so in this way, the final the option you get is x prime. So x prime, y prime, z prime are variable on the other piece. Should be 1 over x and y prime equals x c. And you can check that this is actually OP or minus. X1 plus OP. And you can also check x, y, z equals x prime, y prime, z, which is denoted by w. So I get the commutative lambda Hansol model this side by this Green construction. And yeah, I finished my talk with 2 more remarks. So first of all, is because there are lots of ways of moving these points to these new positions, right? So actually, the meter you get depending on how you move the points. So if you do some different move, then you have another coordinate change. So you could have the meter space. It seems to depend. So yeah, if you in certain case we checked you may have O minus 2 plus O instead of minus 1 comma minus 1, and that and yeah this part I didn't quite understand. And second remark is you can actually transform Lagrangians too. So, for example, if you have Lagrangian, non-compact Lagrangian like this, and you do a transform on each piece, and then you have a module or matrix factorization on each chart. And to identify them, you do some kind of coordinate change using this kind of configuration. So you get a fine but global matrix factorization. But the problem is you may have some Lagrangian which doesn't behave very nicely. And there's, I think, but Heather Lee, for example, she chose a set of very nice Lagrangians, which doesn't occur a very serious problem when you group. So I think we could use this generating set as well. And, yeah, and it's still work in progress. So yeah. Anyway, I'll stop here.
Question?
So in this non-commutative mirror, if you take the commutative thing with the same potential, do you know what happens?
I take commutative thing with the same potential.
Yeah.
So you force this to be just commutative.
Yeah.
By imposing this potential.
So it just doesn't work, or?
Yeah, even yeah, I think that loses some information. And that is somehow looking at smaller deformation space, right? The impose more relation means my mirror space, which is smaller deformation space, becomes smaller and smaller. So I expect that may lose some information. But yeah, I'm not sure.
example, if you impose just impose the commutative relation x y equals to y x, right?
Oh yeah.
Then you just kill the space.
Yeah, I think if you impose this commutative relation here, then for example you declared xy equals yx. But these are like loops based at different points, but they cannot be the same. So I think you just end up with zero edge, at least in this example. I don't know what it
I
was.
think it's the difference between when you look at this Monod-Cartan equation, you can either consider your variables being non-commutative or commutative. They all make sense because the Monod-Cartan is actually symmetric.
Yeah, but our point of view is usually if you only use commutative variables, then you may not have any solutions. So this is why you want to enlarge the deformation space by allowing
Actually,
non-commutative variables.
no. If you take the commutative variables, you'll get actually all weakly unobstructed, right? Because this extra part are all symmetric, right? X, Y, Z, Z, Y, right?
In this example, there are two Lagrangians.
Because unit is here like union of. So I have two Lagrangians. L is a union of two Lagrangians.
So you have to consider the path algebra, which has to be non-commutative. Just like x, y, and y, x are different path loops at two different points.
Have a question? No, that's thanks, speaker.